Hello everyone, we are solving the tutorial on Opamps. So in the first question of the assignment, question 1a, it is given that you have a circuit like this. The non-inverting terminal is grounded and the inverting terminal receives three branches each having voltages capital V1, V2, V3. The resistors are R1, R2 and R3. There is a resistor that is RF. Question is to obtain V0. So there are two things that we have to keep in mind while solving any op-amp question. One of them is that the op-amp does not draw any current. This is because the op-amp has a very high input resistance. A consequence of this is that you just need to write KCL at the input node. Means you need to apply KCL at the input node. In this case, this is that node. This is the inverting terminal. So we call it V2. Non-inverting terminal node potential is called V1. So I just have to apply KCL at this node, and because the op-amp does not draw any current, whatever is the current coming into this node, the entire amount flows into the feedback circuit. And the second important aspect is the concept of virtual ground. The concept of virtual ground says that the difference between the input terminals V1 minus V2 is almost zero. This tells us that V1 is nearly same as V2. So for example, if V1 is grounded, that means V1 is 0, then V2 is also 0. So using these two ideas, we can solve any op-amp question. The third point one should remember is that suppose you have multiple inputs. So if you have multiple sources, in different terminals, you use superposition by reducing the circuit to a standard configuration. Superposition means that if you have multiple sources, the output will be the sum of output if just one of those sources was active. So if there are multiple inputs in multiple terminals, say if there was an input in the inverting as well as non-inverting terminal. So what you could do is you suppress one source and find the output for the one source that is active. Now, when you suppress the other source, you've reduced the circuit into a standard configuration. Say if you suppress the inverting terminal input, then you've converted this circuit into a non-inverting configuration. An example of this is making the differencing amplifier, which was discussed in the previous lecture. So please go through that. A majority of questions will be solved using these two concepts. So since the op-amp does not draw any current, if I write the equation of these three currents, let me call this I1, I2 and I3. So I1 plus I2 plus I3, I1 plus I2 plus I3 should be equal to IF. It is the current through the feedback resistor. We would have typically written I1 plus I2 plus I3 should be equal to IF plus this base current, whatever flows inside the op-amp. But since op-amp does not draw any current, that term is negligible. I can write I1 as capital V1 minus node potential V2 upon R1 plus I2 is capital V2. Capital V2, capital V1, V2, V3 are the input signals. So capital V2 minus node potential V2 upon R2 plus capital V3 minus node potential V2 upon R3. This should be equal to IF. IF is V2 minus V0 upon RF. This is one equation, and by virtual ground, we can say that since V1 is equal to 0, V2 is also equal to 0. So just plug in the value of V2 in this equation. We get minus V0 upon Rf is equal to V1 upon R1 plus V2 upon R2 plus V3 upon R3. Taking this Rf to the other side, along with the minus sign, we have minus Rf upon R1, Rf upon R2, Rf upon R3. Essentially, this is a weighted summation of the three inputs V1, V2, V3, the respective weights being Rf upon R1, Rf upon R2 and Rf upon R3. There's a negative sign because this was connected in an inverting configuration. If suppose Rf was equal to R1, R2 and R3, in that case these terms would have cancelled out and you would have got a simple addition of the three terms with a negative sign. This would be true even if you had n number of inputs here. You could have had many other terms here. This type of an amplifier is called a summing amplifier. So you could have, instead of this, you could have had a circuit like this, which has n inputs, V1, V2, V3 and so on up to Vn. Resistors are R1, R2 up to Rn. So here you would have terms like Rf upon Rn times Vn, and the output would be a summation of all these. Again, if the feedback resistor was equal to all these other resistors, you would have got V1 plus V2 up to Vn. And this is what is called a summing amplifier or a summer circuit. These two concepts are important and we'll be using them to solve all the questions of this assignment. This was question number 1A. Going to question 1B. Here also you have to find output and the circuit is something like this. So the same logic, write the currents. So this is I1 and this is IC. I1 is equal to IC in this case. Node potential at the inverting terminal is V2. This is V1. Note that this is lowercase v1, which is representing the node potential at the non-inverting terminal. The uppercase v1, capital V1, is representing the input signal. So if I had to write the expression of I1, that would be V1 minus V2 by R. We know that the current through a capacitor is given as C dV by dt, where V is the potential across this capacitor. So here it would be C dVc by dt, where this is Vc. So Vc can be written as V2 minus V0, and this is equal to V1 minus V2 by R. Now by virtual ground, V1 is equal to V2, which is equal to 0. Plugging in that here, we get V1 by R is equal to minus C d V0 by dt. Now here we've got an expression in terms of derivative of V0, but question asks us to find V0. So to find V0, we'll have to do integration on both sides. So integrating both sides would give us V0 is equal to 1 upon RC, integration from minus infinity to t, V1 dt. So you notice that this kind of a circuit gives us an output which is equal to a constant multiplied by the integration of the input. So if somehow we were to get the product of RC equal to 1, this circuit would work as a simple inverting integrator. Because there's a minus sign, that's why inverting. This is an application of op-amp as an integrator. Whatever is the input, the output is the integration of that signal. We go to the next question. Determine the output for the circuit shown in the figure for a sinusoidal input of 2.5 millivolt. So it is given that Vin is 2.5 millivolt. The circuit is something like this. This plus 9 and minus 9 given in this question just tells us that the output cannot exceed plus 9 and cannot go below minus 9 volts. So we can see that this is a very simple inverting amplifier with negative feedback, because the feedback is given to the inverting terminal and input is connected to the inverting terminal. That's why it's negative feedback in inverting configuration. We already know that gain for such an amplifier, which is output upon input, is minus RF upon R1. Here we can see that RF is 200 kilo ohm and R1 is 2 kilo ohm. So I'm not writing kilo ohm because it gets cancelled. So this circuit has an inverting gain of 100 or a gain of minus 100. So this tells us that output will be gain times input. So minus 100 times, it says that the input is 2.5 millivolt. This gives us minus 250 millivolt or minus 0.25 volt. This is the answer. It's very important to understand that when you are connecting any circuit in feedback, we are calling it negative feedback because the feedback circuitry or the feedback resistor comes back to the inverting terminal. That is why this is negative feedback. That is how we saw in the first lecture how giving this kind of a feedback actually contributes to reducing the effective value of difference potential Vd, right? So it's important that when we are calling it negative feedback, the feedback is connected to the inverting terminal. Now, depending on which terminal the input signal is connected, this amplifier becomes an inverting amplifier or a non-inverting amplifier. Okay, but the feedback remains negative. Feedback remains as negative feedback. This is something you should take a note of. Question 3. Question says find the output and the circuit is something like this. It has another stage. It has a third stage. So this was end of stage 1. This is end of stage 2. This is output. This is RF. This is R1, R2, R3. Given RF is 470 kilo ohm. R1 is 4.3 kilo ohm. R2 is 33 kilo ohm and R3 is also 33 kilo ohm. We have to find output. So clearly, if we look at this overall circuit, we can say that these are 3 stages of closed loop amplifier configurations. So if we look at the first stage, this is a non-inverting closed loop amplifier, right? Let us say its gain is some AF1, the overall gain of this stage. The next stage The next stage is this. The input to the inverting terminal of this stage is the output of the previous stage. So clearly, this is closed loop inverting amplifier. Let us say the gain of this stage is some AF2. Now the output of this stage is fed to the third stage. So here you have input connected to the non-inverting terminal. So this is again an inverting closed loop amplifier. Because we have a negative feedback. We have negative feedback in all three, right? But the first one had an input connected to the non-inverting terminal. That's why this was non-inverting amplifier. The second and the third one are inverting amplifiers. We already know that AF1 for a non-inverting amplifier, the gain is 1 plus RF upon R1. This is RF and this is R1. For an inverting amplifier, gain is minus RF upon R1, and here the value of R1 is R2. The gain for the third stage, AF3, would be minus RF upon R3. And we also know that when we have three stages connected in cascade, the overall gain of three stages connected in cascade would be the product of individual gains. So this would be AF1 into AF2 into AF3. This tells us that the overall gain V0 upon V in, this should be equal to AF1, that is 1 plus RF upon R1, into AF2, that is minus RF upon R2, into AF3, that is minus RF upon R3. You plug in the values of RF, R1, R2 and R3, you should get a value 22.2 into 10 to the power 3. Now knowing that V0 upon Vn is 22.2 into 10 to the power 3, it is given that the input is 80 microvolt. So given that Vin is 80 microvolt, output would be overall gain multiplied by input, which is equal to 1.78 volt. This is the output. All right, question 4 gives a circuit like this. Now there is a diode connected in the feedback loop. Some voltage Vin is given as the input to this circuit. This is R. Let's call the drop across the diode as Vd, V capital D. And output is measured at this node with respect to ground. So question says, find the output of the op-amp circuit. It is also given that this diode, which is connected in the feedback circuit, it has a reverse saturation current of Is such that R times Is is equal to 1. So this R times the reverse saturation current of this diode is equal to 1. Now this might have some use later on, right? So let us first just solve the question. The question also asks, what mathematical operation does this circuit perform? So first let's just find the output. So let the current flowing in, let that be I1. Let the current flowing through the diode be ID. Since the op-amp does not draw any current, I1 is almost same as ID, or we can say equal to ID. Node potential at the inverting terminal is V2. At the non-inverting terminal is V1. So we can say I1 is Vin minus V2 by R, and this should be same as ID. Now the current through a junction diode is given as Is e to the power Vd upon eta Vt. Now I'm also assuming that eta is equal to 1 here. So I'm just writing it as Vt. Here Vt is the thermal voltage and its value is almost 25 millivolts at room temperature. It's a constant for a given temperature. Now this is one thing that we know. Now what is Vd? Vd is the potential across this diode, potential of P side with respect to N side, correct? So I can say Vd is simply V2 minus V0 because P side is connected to V2. So if we rewrite this, it would become, instead of Vd, I can write V2 minus V0. Now by the concept of virtual ground, V2 is nearly at the same potential as V1 and V1 is connected to ground. That means V1 is 0. That tells us V2 is also 0. So plugging in the value of V2 in this equation gives us, so this is same as V1 upon RIS is equal to e to the power minus V0 by Vt. Now remember we have to find output V0. That means we want something of the form V0 equal to some expression, right? So a logical way to do this would be to find natural logarithm on both sides. So we get this is equal to log of e to the power something. So that's same as the exponent. So we get minus V0 upon Vt. So this gives us V0 is equal to minus Vt times log of Vn upon Ris. But it's given that Ris is equal to 1. So I'm plugging in Ris equal to 1 here. So we get V0 is equal to Vt log of Vin. Remember that Vt is a constant for a given temperature. So this is the output. So the part of the question that says what mathematical operation does this circuit perform? The answer is that this is a logarithmic amplifier. So whatever is the input, this circuit finds the logarithm of that input and multiplies it with the thermal voltage at that instant with a negative sign. So it's an inverting logarithmic amplifier. Understand that input being given to inverting terminal by default means that this is going to be an inverting amplifier. Now we should note that to make this a logarithmic amplifier, we can actually choose the value of R because we know the value of reverse saturation current for a particular diode from its data sheet. So to make sure that R into Is is equal to 1, we can choose an appropriate value of R here. Moving on to question 5. It's a similar circuit as in question 4, but the positions of the resistor and the diode are interchanged. So you still have an inverting input, means input is connected to the inverting terminal. The input is Vi. In the feedback loop, you have a resistor. This is a negative feedback because the feedback is connected to the inverting terminal. This is output. Question says find the output for this circuit given that the reverse saturation current of this diode is some Is. Again, what is the mathematical operation that this circuit performs? So we follow the same procedure because the op-amp does not draw any current. ID is same as IR. Current through the diode ID can be written as Is e to the power Vd by Vt. Eta Vt, I'm assuming eta is equal to 1. This should be equal to IR and IR would be V2 minus V0 upon R. Vd here is the potential across the diode. That means P side with respect to N side, which here can be written as Vin minus V2 divided by Vt. This should be equal to V2 minus V0 by R. Now by virtual ground, we know that V1 is same as V2, and since V1 is grounded, V2 is also equal to 0. Plugging in V2 in the previous equation gives us Is e to the power Vi by Vt is equal to minus V0 by R. Therefore, V0 is minus Ris e to the power Vi by Vt. This is the output, meaning given an input Vi, this kind of a circuit does exponentiation. So it's an exponential amplifier. Given an input, It finds the value of e to the power that input multiplied by some negative constant. So this is an exponential amplifier. If we were not taking eta equal to 1, everywhere we would have carried the term eta. Question 6 now. Question 6 says, having now at your disposal the two amplifiers of questions 4 and 5, that means the exponential amplifier and the logarithmic amplifier, devise a circuit that multiplies two numbers together. You can also make use of any other amplifier that we have learned so far. We need to make a multiplying amplifier. So we need to make a multiplier such that if there are two inputs, say V in 1 and V in 2, the output V naught should be a product of these two inputs. Okay. So we know that log of A plus log of B is equal to log of AB, and e to the power log of AB is equal to AB. Now we already know that individually these operations can be done by logarithmic amplifier of question 4. We know that adding them together can be done by the summing amplifier of question 1, and this operation can be done by using the exponential amplifier of question 5. So we would need 4 opamps for this purpose, 2 as logarithmic amplifiers. This is to be followed by a summing amplifier that adds the two log outputs. This is then to be fed to an exponential amplifier to perform e to the power log AB, which is AB. So remember that a logarithmic amplifier has a diode in its feedback circuit. So the output of the first logarithmic amplifier is, say, something like some minus k, where k is a constant, minus k times log of V in 1. That of the second logarithmic amplifier is, say, minus k times log of V in 2, where k is some constant. This has to be fed to the summing amplifier. So a resistor given as the input to the summing amplifier, again connected in negative feedback and inverting configuration. So the output of this stage would be something of the form, say, some other constant, say C times log V in 1 plus log V in 2. So we've reached the last stage. The last stage should be an exponential amplifier. That means it's just like the logarithmic amplifier, but we'll just interchange the position of diode and resistor. This is the exponential amplifier, and as a result, the output would be V in 1 times V in 2. So we'll choose these resistors, say RF2, this is RF1. We'll choose these resistors and diodes so that these constants cancel out, and eventually we are left with just V in 1 into V in 2. Thank you.